Okay, so we're going to start off today introducing something called a relation. Now, what's interesting is what I'm going to show you today is exactly what I show a remedial algebra class. In other words, the mathematics of a relation you're supposed to learn at the very beginning of remedial algebra and a lot of the terminology. Is the Math 46 student going to understand what's going on? Probably not, but they can at least use it. So first of all, in simple English, a relation is simply a set of ordered pairs. That's it. Now, most people confuse relation and function. I don't want to do that. A function is a relation, but most relations are not functions. So don't put those two together yet. So if a relation is simply a set of ordered pairs, where do the ordered pairs come from? So what we have is two sets. We'll call the sets A and B, okay? Now, some of the notation and the terminology I'm going to use is also the same terminology we would use in a linear algebra course, because words do mean the same thing across math courses typically. So we have a relation, we'll call the relation R for relation, but sometimes people confuse the symbol with the R we use for real numbers. And I just want to make sure everybody understands. I will always use a script R. Textbooks will use a kind of a fancy R when they mean real numbers, but I'm using R as my relation just because it's convenient. I could use some other letter of the alphabet. So we would say A, R, B. That's how we do the relation. So what is A and what is B? Well, let's think numbers first of all. So A may be a set of integers. It may be the entire set of real numbers. It may be just 3 values. A is a set, B is a set, and I'm going to do a mapping from A to B, and that's very important, the direction we're going. So what we start off with right off the bat is the Cartesian product A cross B. This would be my universal set, and we talked about that last day. I have a set A, I have a set B. A cross B would be the most number of things I could possibly have. And so we discussed how to create a Cartesian product last day. That's a very simple thing. Then we have a specific relation R, so therefore R will be a subset of A cross B. R might be all of A cross B or just some of the ordered pairs in A cross B, not necessarily all of them. A is called the domain, B is called the codomain. Now be very careful. B is not the range. In baby algebra, you're always taught domain and range, and that's it. No. Range is very special. If I'm mapping real numbers into real numbers, great. But which real numbers did I actually use in my relation? That's what determines the range of something. Okay, which ones did I actually use are the range? But I'm allowing an entire set. I may not use the entire set, and so the notation and the language is if I'm going from A to B, and I end up using all of B, then we would say it is onto. That's where that word comes from. If the range is the entire codomain, then you're onto. Generally speaking, a range doesn't have to be the entire codomain. If I was talking about something like a line, okay, not a horizontal or vertical line, just a line with a slope, and you'd say, well, what y values am I using? You're using all of them. So that one would be onto. But if I said, think of y equal e to the x, I'm not using any negative numbers. Oh, so that would not be onto. Okay, I'm only using the positive values. So my range would not be all real numbers. It would be something less. And so that's from the baby algebra standpoint of relating the two. So my relation is a subset of here, and really it comes down to this. And we'll use x and y just to make it convenient. So x is going to come from A, y is going to come from B. We say that if x comma y is an element of my particular relation, then the notation we would use is we'd say then x r y. X is related to y, okay? That seems like a little bit of overkill, but it's kind of a way of testing things. Now, if the ordered pair is not in R, if this was not the case, then we just simply say it's not related. We just kind of cross it off there. Okay, so let's do a couple of examples because this seems very abstract when actually this should be very, very simple. So let's suppose that A is the set, how about 1, 2, 3, and B is the set 2, 4, 6. Keep it real simple, okay? Then A cross B, we'll start with that, is the set of ordered pairs, and it should have exactly 9 ordered pairs because I'm crossing 3 things with 3 things. So 1, 2, 1, 4, 1, 6, then 2, 2, 2, 4, 2, 6, and then where are we? 3, 2, 3, 4, 3, 6. Okay, great. Now let's define our relation R. Now there's an infinite number of relations that I could define. This is the Cartesian product regardless of what my relation is. Okay, that's that thing we have to understand. My domain is A, my codomain is B. This is my Cartesian product. Now I want to define a relation that uses some or all of these things. So I could define a relation this way. We'll say, and I want to get used to the notation, for all, we introduced this symbol last day, for all xy in A cross B. So in English, for every ordered pair in the Cartesian product, X will be related to Y if, now let's make up something really simple. Let's say that, how about if Y over X is an element of the integers. Capital Z is going to be one of the really common symbols we use. And the reason I put a line through it is because I don't want, my Z's and my 2's can tend to look real similar. So I always make my Z's that way. Now, the set of integers we are very familiar with. Positive or negative isn't important in this case. If it were positive or negative, specifically, we put a plus or a minus. So in English, I'm saying, hey, every x, y, every ordered pair in my Cartesian product, we're going to say that X is related to Y if the quotient Y over X is an integer. So as I'm looking through here, you go, oh, they're all going to be integers, aren't they? Well, no, actually, not all of them are going to be integers. I mean, 2 over 3, 4 over 3. No, some of them won't be integers, but a lot of them will be integers. So if I said now, can you tell me what R is? Well, what would the set R be? R would therefore be the set 1, 2, 1, 4, 1, 6, 2, 2, 2, 4, 2, 6, not that one, but 3, 6. Okay, so R, notice the set R is contained in A cross B. I'll use the formal symbol. Okay. Now, true or false? True or false? 1 R 6. Is that a true? Just blurt it out if you want. Is that a true or false statement based on our definitions and what these symbols mean? Anybody? Mm-hmm. That is true. Why is it true? Because we just said it's in the set. Or it's satisfied this relation. All right. Next. 3R2. True or false?
False.
That's false because we said this is not in the set, so we would write it like that. This is really not complicated, as you can see. Now, when we discuss relations in this manner, we often treat relations as being finite sets so that we can list them and actually talk about it. But my relation might be, my A might be the set of integers, my B might be the set of integers, and I can do the exact same thing. If I said, let's consider the infinite set, A could be capital Z, B could also be capital Z, and I could still define this the same way, but now my relation would be infinitely large, but based on this criteria right here, this determines. Now, we can mess around with this statement all we want and say, maybe we want to say that X plus Y is an even number. Maybe that's our relation. Maybe we say that the difference of X and Y is a multiple of 5. That could be our relation. We can make this up and have an infinite number of relations, but it's a fairly simple thing. Now, function.
Oh, can I ask a really quick question?
Absolutely.
Could you write 6R1, or does it matter that you have the domain and then the codomain?
Good question. Good question. Well, 6 isn't in the domain. 6 comes from the codomain. And remember how we wrote it X, R, Y? So you can't have Y, R, X unless we do something else. And that was a great question, by the way. Yeah, I can only take first element related to second element in that order because our Cartesian product is this way. And we discussed this last day. Cartesian product is not commutative. If I do B cross A, I do not get the same set of ordered pairs in general. I could get the same set of ordered pairs if I made A and B be the same sets, but in general, A cross B and B cross A are not the same sets. But B cross A is something else, and it is an important set. So let's go. I'm going to erase some of this because I don't need all of it. Actually, I don't need any of this for the next thing. Now, when we're talking about relations, now I want to go back to baby algebra. When I say baby algebra, I'm referring to Math 46, Math 96. You have to understand, when a math person refers to algebra, whenever a math person talks about algebra, they're not talking about what you did in 9th grade. They're talking about what you're doing maybe in 3rd year of grad school. In other words, the word algebra to a math person means the highest level of abstract reasoning and the scariest stuff you've ever seen in your life kind of algebra. Linear algebra would be considered the lowest level of algebra when you're talking about algebra on that nature. So I just usually throw in the term baby algebra. So when I refer to, in an upper level class, if I refer to baby calculus, that sounds redundant, I know. Baby calculus, what? Well, think of something like the business calculus. I mean, that's really, really low level math. I hate to say it, it's not what you guys did. It's not real calculus. It's, I mean, can you imagine doing calculus without ever using the word limit? Oh, and avoiding everything trig. Yeah, that's what business calculus is. It's really, it's not even pre-calc. It's probably between intermediate algebra and pre-calc in terms of level of difficulty. So that's not a good one. So a relation in general, we said, is a set of ordered pairs. So if I define the following relation, let me just keep it really simple. My relation is 1, 2, 3, 5, 4, 7. And I'm just going to stop with that because I'm going to add to this. Now, remember, what is the definition of the domain? The domain is the set of first elements, okay? The domain would be, in this case, I'm going to write them down, and not in set form, I'm just going to write them down. Now, because I don't know where this relation came from, I didn't tell you what the Cartesian product was. I didn't tell you what the original A and B are, okay? Then you don't know what the codomain is, but you do know what the range is. The range are the Y values that I actually use. So in this case, you can tell me the range, R and G, and it would be 2, 5, 7. And so what we do is we create what's called a mapping, which is pretty simple. I just draw little arrows. 1 gets mapped to 2. That means 1R2 is a correct statement. 3R5, 4R7. Now that seems redundant because I've already given you my set of ordered pairs, but using the prior notation, that's what this means. Okay, pretty simple, pretty standard stuff. Now, the definition of a function, the simplest user-friendly definition of a function is that each element of the domain gets mapped to a unique element of the range. And the key is unique. Unique means one and only one. It means there is one, but there is only one. That's not the same as saying like there exists, because there exists means there's at least one. To say there exists an answer to my question means that there is an answer, but there might be 2, there might be 20, there might be infinitely many. But to say there's a unique answer to my question says there is one, but there's exactly one. So the word unique is very powerful mathematically. So the definition that we use for a function generally is each element of the domain has a unique In linear algebra, we call this guy the pre-image and we call this guy the image. Those still mean the same thing in this context. So now I'm going to add to my set for the purposes of illustration here. So now I'm going to add, let's say, 4, 9. Okay, so how does that change? Now, we talked about this last day. When indicating sets, the domain is a set. I'm listing it down, but if you said the domain was simply the set 1, 3, 4, this would be a correct way of indicating the domain. I just use another 4. So do I write 4 a second time? No. We said when indicating a set, if something's repeated, you still only write it one time. Okay? That's very important that we understand that. We still only write it one time. So in this case here, I don't write the 4 again, but now I have a 9. So the simple visual illustration here, I have one element of the domain getting mapped to multiple elements of the range. Is this a function, yes or no, based on the definition? Blurt it out if you want. Is this a function? Is this relation a function?
No.
Why not? Because you're right, but you got to know why you're right.
Because it's not one-to-one.
No, careful. That has nothing to do with function. Ooh, I'm glad you said one-to-one and function are not the same thing. Function, if you're one-to-one, you're a function, but if you're a function, you're probably not one-to-one. If you think algebra. Yeah, well, those are completely different animals. No, because what did I say about unique? Every element of the domain has a unique image, and this doesn't. This went to 2 different values. Now, when we teach this in baby algebra, we usually also do it graphically. So if you remember graphically, that means if I plotted these ordered pairs, what would I notice? That 4, 7 and 4, 9 would be located vertically. Does that ring a bell? You go, oh yeah, the old vertical line test, that kind of thing. If I can draw a vertical line passing through more than one point, it fails. Why is that? Because it meant one input produced multiple outputs. That's what that means. That's the baby algebra version, and it's still just as correct for us. I just don't need to draw a picture. All right, now let me tweak it again. Okay, so I'm going to change this. So now I just added another point, 6, 7. Now, is this a function? Now, someone asked about one-to-one. This is not one-to-one. But is it still a function?
Yeah.
Yes. That's why I said never confuse one-to-one with function. Yeah, if you're one-to-one, you're a function. But if you're a function, you're not necessarily one-to-one. One-to-one would be a subset of function. This is not one-to-one because one-to-one means each element of the range came from a unique preimage. But that's not a criteria that we need. Each element of the domain still only had one arrow leaving it. You can think of it that way. So this is still a function. Okay, so this one's okay. This is a function. That doesn't violate any rules. And sometimes we forgot that reason. Okay, so each input has a unique output. Now, it is typical now, again, I'm using the baby algebra approach because it's not different. If I said R inverse, I'm not raising R to the -1 power. R inverse is not the reciprocal. The only time reciprocal and inverse are the same thing is when we multiply. That's why a number raised to a -1st power is its reciprocal. But all other situations, the -1 just means inverse. R inverse. This is, by the way, the formal definition at every level of mathematics. The definition of the inverse of a relation is input and output just simply swapped places. My inputs were 1, 3, 4, 6. Now those became my outputs. So that's the definition of inverse. Now, this R here is absolutely guaranteed to be a function. Is R inverse a function?
No.
No. And now you could go back to the previous. If a function is not one-to-one, then its inverse is not a function, because if in this case here, these 2 points were located horizontally. So therefore, when I swap the roles of x and y, the inverse they'd be located vertically. The simplest example, think of a parabola, right? A parabola we know is a function, but its inverse is a sideways parabola, which is not a function. Oh, okay. That kind of rings a bell. Now, I don't want to get into the algebra because that's what we do in the calculus when we do all that stuff. But I want you to be familiar with some of the terminology, and makes it fairly simple. We don't use the word range in this context of talking about relations, because you're always going to be given your original 2 sets, your A and B, call them, and then you're going to take the Cartesian product, produce your universal set, and then from those you're going to use some or all of those ordered pairs. So you're always going to go from domain to codomain. Remember, the ones you actually use, that would be called your range. But in general, right, you're going from domain to codomain. In algebra, we went from real number to real number. Always in baby algebra. We didn't go from real number to imaginary number. We didn't go from real number to integer. We went from real numbers to real numbers. But depending on the function you defined, you may or may not have used the entire codomain. Again, think of something like an exponential function. That doesn't use the whole thing. But or something as redundant as a horizontal line, right? That only uses one value in the whole set of real numbers. But I'm still I'm going from real numbers to real numbers. Okay, so before I continue, does anybody have any questions on this? Let me just wave at me if you have any questions, because we're now going to change up to a very different topic. Anybody at all? You can speak out. Okay, there's nothing about this that you should find tremendously challenging, by the way. And this should be fairly simple stuff. Now we're going to start the logic part. And this stuff is very notation oriented too. Symbols are very, very important in this case. Okay, so I'm going to start with the concept. And one of the things I like to do in any math class is use the same symbols over and over again to mean the same things. If we're in algebra and we're graphing in X and Y, I don't want to tomorrow now graph in A and B and then the next day graph with C and D. No, I'm going to continue with X and Y because there's a familiarity. Okay, I don't need to keep changing what we're calling the horizontal and the vertical in an algebra class. That just confuses people. So here we tend to use the same things over and over again. So we typically will use things like P, Q, and R over and over and over again to mean the same things. So I'm going to call P and Q are going to be statements. P might be, and I'll give you some very specific one. P might be, I like oranges. That's my statement. Okay. A statement is either true or it is false. It's not ambiguous in any way. Okay. So that's why to be a statement, it has to be something that, yes, this is true, this is false in the situation here. The statement might be, I am enrolled in Math 245. Well, that's either true or it's false. It's not a maybe. Okay. Now, given the statements, and we're going to start with just 2 statements, we now want to talk about, well, what if both of them are true? What if only one of them is true? What if neither one of them is true? How do we say that mathematically? So for those of you who are computer science people and programmers, there's 3 words that are extremely important. These are 3 of the most important words if you're a programmer. Okay, and, or, and not. Not probably the most important of all of them. And I want to go over what they mean in this context. So first of all, and. All right, if I said, I like pizza and I like football. Now, for this statement to be false, if you found out I didn't like pizza, but I did like football, then my statement isn't true, because I said I liked both of them at the same time. For an and to be true, and by the way, whether you have 2 statements or 2,000 statements, it's the same rules. For an and to be true, every part of the and has to be true. So we say this is very exclusive. And another term that we use for and, by the way, is intersection. We use if I'm talking about sets, if you're in set A and you're in set B at the same time, then you're in the intersection of A and B. So using a Venn diagram, This is the part that's in A and in B at the same time. So a lot of you are familiar with that. But we want to talk about it from a logic standpoint, not from a set standpoint. We are going to talk about the set theory later on in the course. Now we're just going to talk about in terms of logic, just simple statements. So I always say for an and to be true, all parts of the and. So this is the example I always give in my low-level math classes, okay? I'm going for a job interview. Now, like any good job interview, if you do it right, you're actually interviewing the people that want to hire you. You're interviewing them to see if they're worthy of your talents. So I'm sitting down at this, long table of people that look scary in business suits, and I say, before we start, I'm going to make my list of demands. Okay, I want a 6-figure income, keys to the executive washroom, my own parking space, and the letter M stricken from all company language. That's before we even start the interview. And so they get together, they think about it, and they say, well, we can do everything except the parking space because it's kind of limited. Will I take the job? Anybody? Yes or no? This is an absolute. Will I take the job? I said, I gave them 4 demands. I want this demand and this and this and this. And they said they cannot do one of them. Am I taking the job?
No.
No, because I used the word and. And is absolutely exclusive, which means if any part of an and is not true, then the entire statement is not true. If I am over here, but I'm not in the intersection, then I'm not in B. I'm not in both of them. So that's what the and statement is. Now, or is very inclusive. If any part of an or is true, then the or is true. So I'm going to have breakfast later on today, or I'm from Mars, or I'm going to fly to the moon this afternoon. Now, after you see me have breakfast later on today, then what I said was true. I didn't fly to the moon and I'm not from Mars, but I did have breakfast. So the or was true. Okay. So the point being that the words or and are absolutely critical that you interpret them correctly. So if I said I'm in A or I'm in B, then any part of this would be true. And A, in that sense, erase them. It's getting harder to erase as I write. Or often we refer to as the union. So if any part of anything is true, the or is true. Now, symbolically, what we do for an and for a statement, we use this symbol. For an or statement, we use this symbol. Now, right off the bat, so well, that's totally confusing. Actually, it's not that confusing because with sets, if I said I am in the intersection of sets, we use this symbol. And if I'm in the union of sets, we use this symbol. So everyone sees they're kind of related. One's pointing up and one's pointing down. So when I'm talking about sets, then we say intersection union. I'm not talking about set, a collection of objects in set A, a collection of objects in set B. What is the intersection? Which objects are in both sets? That's something else. That's set theory. Again, we do that a little bit later in the course. We're just making logical statements. I'm going to the store today. I'm going to drive my car today. If I go to the store and I drive my car, that's not an intersection, but I would use this symbol. Okay, so this is the and, this is the or. So up here, if I said P, this statement here means P and Q are both true. This statement here means P or Q are true. One of them is true. They could both be true, by the way, but definitely one of them is true. So you can say at least one of them is true. Okay, so that's what it means. When I have a statement, I just simply have a statement. My statement is true or my statement is not true. Now, the last one, which is probably the most powerful one, is the not. And here's where people get in trouble all the time because we overthink. Okay, I'm going to use a term, compliment. Now, I don't mean you look nice today. Now, that would be spelled with an I. That's, I'm giving you compliments. No, compliment, I like to think of as the logical opposite of something. Mathematically speaking, compliments are absolutely huge. If you've ever had statistics, if you've completed a Math 119 course, you're probably very familiar with the concept of a complement. A complement, I like to say, is the logical opposite. And if you have a finite set, another way of saying the complement is everything else. You see? So if I said, okay, here, hold on a second. I have a glass of water. What is the complement of a full glass of water? Anybody want to try that one? What is the complement of a full glass of water?
Empty glass of water.
Great guess. No, that's called the antonym. That's an English term. Here's the problem. How many states could this glass be? It could be full, it could be almost full, all the way down to empty. Would you agree there's an infinite number of possible states the glass could be? We all agree there's an infinite number of levels of fullness. Yes. And so therefore, what's the complement of full?
Not full.
Not full. By the way, does empty fall in the category of not full? Yes, but so does half full. So a glass of water is either full or it is not. And I have just covered all possibilities. This is why complement is difficult sometimes, because we think of antonyms. In other words, we're math people, we make everything binary. And that's dangerous. There are times when it is binary. You see, the light switch is on or it is off. My statement is true or it is false. I'm writing computer codes, either 1 or it's 0. Life is good when it's binary. I'm filling out a multiple choice test. It's A or it's B or it's C or, oh shoot, it's A or it's not A. Oh, now it's binary. So what complement does is it makes everything only 2 choices. And you've heard, there are only 2 types of people in this world. There's only 2. There's Rebecca. And then what? Well, the rest of us. Is that a true statement mathematically? Yes, because every one of you is either Rebecca or you're not. So that's the thing about complements. If I'm looking at a classroom and I say, what's the complement of people in this particular row? Now that can be a little bit ambiguous because, wait a minute, who's not in that row? Are we talking about planet Earth? Are we talking about the state of California? No, so I first always have to identify my universal set. So if I said, I am considering the people in this class, now, what is the complement of this group of people? It would be everybody else in the class. It's not in that group of people. Because together, something in its complement together make up the whole. And we're going to talk about how this works a little bit later when we get to conditional statements, because the concept of contradiction comes from the word complement. So complement just means everything else, and the simplest way to state a complement is whatever you say, the complement would be not. Everybody got that? That's it. The glass is full or it's not full. What you see, if I said, all right, look at where you're sitting right now. What is the opposite position of where you're sitting right now on planet Earth? Is there a place on planet Earth that's the opposite place? No. So if I said, what's the complement of you're sitting right there? You're not sitting right there, meaning you're sitting somewhere else. But there's not a single value or a single location that would be the complement. The complement would be everything else. So the easiest way to say complement is just not. So symbolically, it's a squiggle, but it's a squiggle in front. So I went to the grocery store today. The complement would be, I did not go to the grocery store today. Not that I went somewhere else. Careful with that. You see, I went to the grocery store. I didn't go to the grocery store. I bought eggs today. I did not buy eggs today. You don't try to come up with something else. It's just not that thing. Now, in statistics, those who've done statistics, we use different symbols for complement, and that usually depends on the textbook. But in statistics, we're usually talking about complements of sets. So if I were to, roll the dice, I rolled the dice and I got a total of 12, I got double sixes. Well, what's the complement? Well, that would be every other dice roll other than that. So one of the reasons we like doing complements when we get to the numerical calculations is sometimes if I ask you something, what's the probability of this thing, or how many ways can I do this thing? That can be a complicated calculation, but the complement of that thing might be something really short and sweet and simple. So it's oftentimes easier to calculate the complement and then just subtract it from the whole. And we're going to find that that's a very valuable tool. Again, those who've had 119, you're probably very, very familiar with that concept. Now, that doesn't come up in this class till much, much, much later in the class. So this would be not P. So right off the bat, let me just throw some statements at you. All right. So let's say statement P is Biff is enrolled in math. Statement Q, Biff is enrolled in English. And statement R, Biff is enrolled in chemistry. All right. So I have three statements. They are either true or they are false, each one. Biff is in math or he's not in math. Real simple. So I would like you to represent symbolically Biff is enrolled in math or English, but not chemistry. Remember, each one of these is true or it is false. I'm not saying P is true. I'm saying Biff is enrolled in math or Biff is not enrolled in math. So we usually start with a positive statement. Therefore, if Biff is not enrolled in math, we just say not P. Now, how could we say this? I want everyone to try this on your own for just a minute. Okay? There's not a whole lot of options, but there are three symbols that I just introduced: the and, the or, and the not. I'd like everyone to try this. And if you want, just write it down on a piece of paper and hold it up. Very close, very close. Is that Kenny? Kenny Lee, very close. You're missing one symbol. Now I'm going to go back to gallery view for a second there so I can see everybody. If you think you've got it, wave at me and then hold it up. Omar, can you hold it closer to your screen? I can't quite see it. Beautiful. Okay, hold on a second. I'm going to pin Omar. Hold on. Don't go away yet. There we go. Can everyone see this? Beautiful. Okay, that was your 15 minutes of fame. Now let me go back. Hold on a minute. Let me go back to myself here. Whoops. It's not letting me pin me now. All right. Okay, this is driving me nuts. Give me a second. It's minimizing my screen. Back to gallery for a moment. Okay. For some reason, it is minimizing everybody else. Okay, now let me go full screen here. Now, I don't know about you guys, but for some reason on my screen, I'm only small. Okay. Oh, by the way, everyone, make sure you are muted for the moment. It's killing me here. It's not letting me pin myself anymore. There we go. Oh, well, no, still not letting me do that. All right. For some reason, I have two people on my screen, and I don't have me on my screen anymore. Well, that was a mistake trying to do that. All right. Okay, well, whatever's going on here, can everybody see the whole screen here or no?
I can.
Is everybody seeing me? Or are you seeing the whole?
Yes, we see you, but we don't see your screen.
You've seen the whole Hollywood Squares. This is really funny. I've never had this happen before. It will not let me have the whole screen anymore.
I pinged you, so
And I think it's because, Omar, you need to mute yourself. I've been getting Omar for the last 3 minutes. I can't seem to un-Omar, so I still have only Omar on my screen. I don't know why. My computer really likes Omar. Let me try one more time. Nope, I can't seem to get rid of Omar. Okay, so we're going to just share the screen for a moment. So the idea here is there's one word here that's a tricky word. Okay, but so first of all, Biff is enrolled in math or English. I think we all agree that's P or Q, but not chemistry. In other words, I'm throwing in there not chemistry. But it's got to be an and because I'm not giving you the choice. This is in addition to this. So this would be an and. Now, here's the problem. I've got all these symbols. Does it matter what order I have them? Yes, because if I group these or group these, so the parentheses, I love that effect. This and not this, as opposed to, if I move the parentheses around, that can actually change things. And so we don't want to do that. Okay. Okay, now let me try this one more time. No, I just got somebody else. This is one of the main reasons I really, really hate Zoom, because Zoom has a mind of its own. The only thing worse than this is when you do a share screen. If you guys have ever done a share screen, you have no idea what's going to happen at some point. Don't even go into breakout rooms. That's even worse. So this is a very simple statement, but basically we are looking at this and saying, how do I say this symbolically? Okay, so but and really are the same thing. Okay, so I have this and this and this, but this would be, that thing is its own separate thing that you've added on. And because you'd say but is an English thing. What if we said this? Biff is enrolled in math or chemistry, or math or English and not chemistry. That would be the same thing. That just, from an English standpoint, sounds kind of odd. Now I'm going to introduce something that's a very, very powerful tool for this in general, and it's called a truth table. Now, most of you have probably never seen one. I think the only area I've ever heard of truth tables being introduced are actually in philosophy, strangely enough. If you've had a philosophy class where your instructor actually has a math background of some sort, you may have learned about truth tables, but it's about the only place I've ever seen. Now, a truth table it's a symbolic representation. If I make a statement, is it equivalent to another statement is really what it comes down to. Are they exactly the same statement? So I'm going to give you an example. If I said to you, is not P and not Q equivalent, and I'll show you the symbol, equivalent to not P and Q. Now, the symbol for equivalent we use generally in this context is we use 3 bars, which can be confusing because we also use 3 bars to say is defined as. But in this context, if P is a statement and Q is a statement and they're saying the exact same thing, we'd say they are equivalent statements. We wouldn't say equals because there's no numerical value, there's no counting. Even with sets, if 2 sets are quote unquote equal, it's because they have the exact same elements. There are actually things involved. But if I make a statement, okay, and I make a different statement, but those 2 statements are essentially saying the same thing, then we say they're equivalent statements. So the question I'm asking, another way of saying it, is not P and not Q equivalent to not P and Q? And the way we do this is with what's called a truth table. And so what a truth table is we write down every possible true and false outcome. I'm going to leave this here and erase the other stuff because I need the space. We write down every possible outcome of P and Q and not P and not Q and all these things. And then we compare the column in the truth table for this statement, and we compare the column in the truth table for this statement. If the truth tables indicate the exact same things in terms of truths and falses, then we say they are equivalent. So I'm going to show you how that works. It's a really simple process, and there's no algebra involved. So we'd start with, okay, I have P, I have Q, I have not P, I have not Q, I have P and Q, I have not P and Q. I'm running out of room here. And then the last one would be I have not P and not Q. You notice I have to build them up. I have to have P and Q before I can have, I'm sorry, I have to have P separate from Q before I can have P and Q. And I have to have P and Q before I can have not P and Q, because we're going to change the order of trues and falses. So in this position here, I actually have so 1, 2, 3, 4, 5, 6, 7 columns. We're only looking at those two to determine if this statement here is true or false. In other words, are they equivalent or are they not equivalent? This is my scratch work to get to this. No way around it. Now, the order I put things down, I could have changed the order. I could have put P, not P, Q, not Q. I could have rearranged the order, but as long as I have these two, I want to be the last two things, it's easier to read. So P is true and Q is true, or P is true and Q is false, or P is false and Q is true, or P is false and Q is false. So we notice there's exactly 4 ways I can have P and Q be true and false, and that's all of them. Okay, this would be equivalent to a coin flip. I flip a coin 2 times. It's heads, 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 tails, tails, heads, tails, tails. It's the same idea. Now, look at this column, not P. So P is true, then not P is false. If P is true, then not P is false. P is false, then not P is true. Now, the order you did these can be random. You just have to make sure you have all 4 of these. Now, not Q, that'd be false, true, false, true. P and Q, that means P and Q both must be true at the same time. That's true. But in all 3 of these cases, at least one of them is false. So each of these would be false. Because remember, for an and to be true, everything has to be true. So this is the only one that they're both true. Not P and Q. Well, that's P and Q, so not P and Q, that'd be false, true, true, true. Now, finally, I want not P and not Q. Well, the only one that's going to be true is the last one. All the others will be false. So now we are done with the truth table and we can make our conclusion. Does this column match this column exactly? Nope. Nope. Some of them are different. That would mean that this is not true. These are not equivalent. Think of it this way. Let's say, let's go back to here. Biff was enrolled in math. Biff was enrolled in English. So Biff was enrolled in math and Biff was enrolled in English. So not that. Does that mean Biff was enrolled in neither one? Or is it possible Biff could have been enrolled in math but not English? Biff was enrolled in English but not math. There were other possibilities. So this is not true. So I'm going to change one thing about this. Okay. Actually, I'm going to need to redo this, unfortunately, because I don't think I'm going to have enough room. Oh no, I know how I can have enough room. Here's where I'm going to change it. I'm going to make this 4. That way I don't have to redo the entire table. So if I make this or, okay, then everything else can remain exactly as it was. Not P or not Q. For not P or not Q to be true, only one of them has to be true. In fact, the only time this statement is false is when both of them are false. When are both of them false? Here. All the other times, at least one of them, so all the other times it'd be true. And notice, now they match. That means that this statement is a true statement. These are equivalent. So if I said it is not the case that Biff is enrolled in both math and English, then that just simply means Biff is not enrolled in math or Biff is not enrolled in English. It didn't have to be an and, it turns out it was an or. Now, it turns out this is an extremely important formula that I'm going to go over in much greater detail next day. But there are some very important rules, and there's actually some algebra that are associated with truth tables, okay? So I'm going to stop there. I'm going to leave you with that.